Betz' law states that the maximum efficiency of a wind power machine is 59%. If a machine tries to capture all the energy of the wind, then the wind will simply go around the machine. According to Newton's second law of motion, the force acting on an object is equal to the mass of that object multiplied by its acceleration. For a wind power machine, instead of a particular object, we need to describe the forces on the airflow that is forced through the machine. We can rearrange the common expression of Newton's second law into a form that is useful to describe the interaction of a machine with the wind. A force can be expressed as a mass flow rate multiplied by a change in velocity. This is the same expression of Newton's second law that is used to describe the thrust produced by a jet engine. The mass flow rate through a wind power machine is equal to the air density multiplied by the area of the machine multiplied by the velocity of the air flowing through the machine. The machine captures wind energy by changing the velocity of the air mass that flows through it. On the upwind side, a wind-powered machine applies a force that deaccelerates the incoming air mass. Upwind of the machine, the velocity of the air mass is equal to the wind velocity, W. I have defined the velocity of the air flowing through the machine to be equal to V. The change in velocity is V minus W. Therefore, the force applied by the machine on the air mass is equal to the mass flow rate multiplied by V minus W. It is in the opposite direction of the wind. In reaction to this force, the wind applies a force on the machine that I have named push. According to Newton's third law of motion, push is equal in magnitude to the force applied by the machine and is in the opposite direction. On the downwind side of the machine, the wind applies a force that pulls the air mass out of the machine and through the machine's wake. I have named this force pull. Inside the machine, the velocity of the air mass is defined to be equal to V. After being pulled through the machine's wake, its velocity is equal to W. The change in velocity is W minus V. Therefore, the pull force is equal to the mass flow rate multiplied by W minus V. The wind pushes and pulls air through the machine. The machine opposes those forces. That is how the machine captures energy from the wind. Power can be defined as the product of a force acting on an object multiplied by the velocity of that object. The total force that the wind applies to the machine is push plus pull. The wind power that the machine captures is equal to push plus pull multiplied by V. The wind power available to the machine is the power that flows through its area when the machine offers no resistance to the wind. Efficiency is defined as the ratio of the wind power captured by the machine to the wind power available to the machine. This can be simplified to express efficiency as a function of the ratio of V to W. A graph of that equation shows that efficiency is maximum when the ratio V to W is equal to 2/3. The efficiency at that value is about 59%.